Lyman alpha emitter galaxies announce themselves through a single powerful spectral signature, a line of ultraviolet light produced when electrons in hydrogen atoms fall from the second energy level to the ground state. In the nearby universe, this transition is unremarkable, easily absorbed by dust and gas, but in the early universe, it becomes a beacon. Lyman alpha emitter galaxies, often abbreviated LAEs, are typically small, young, and vigorously star-forming systems whose intense ultraviolet radiation ionizes surrounding hydrogen. As this hydrogen recombines, it emits Lyman alpha photons in great numbers. Redshift stretches this ultraviolet line into the optical or infrared bands, allowing astronomers to detect these galaxies across vast cosmic distances. LAEs are among the most important traces of early galaxy formation because they are visible at epochs when the universe was only a few 100 million years old. At these times, galaxies were assembling rapidly from cold gas flowing along the cosmic web. Their stellar populations were young, dominated by massive stars that burned hot and fast, flooding their surroundings with ionizing radiation. In such environments, Lyman alpha emission can be extraordinarily strong, sometimes contributing a significant fraction of a galaxy's total luminosity. The line itself often appears asymmetric, with a sharp drop on the blue side due to absorption by intervening neutral hydrogen, and a red wing shaped by scattering and outflows, encoding information about gas kinematics and the surrounding medium. The escape of Lyman alpha photons is anything but straightforward. These photons resonate strongly with neutral hydrogen, scattering countless times before either escaping or being absorbed by dust. As a result, Lyman alpha emission is exquisitely sensitive to the structure, motion, and composition of gas in and around a galaxy. Even small amounts of dust can dramatically suppress the line, while galactic winds can shift photons out of resonance, allowing them to escape more easily. For this reason, LAEs often show evidence of outflows driven by stellar feedback, with expanding shells of gas clearing channels through which radiation can leak. The very presence of strong Lyman alpha emission implies a porous or dynamic interstellar medium, shaped by the violence of early star formation. Beyond individual galaxies, LAEs serve as probes of the intergalactic medium itself. During the epoch of rationalization, much of the hydrogen between galaxies was still neutral, capable of absorbing Lyman alpha photons. As a result, the visibility of LAEs declines sharply at redshifts where the intergalactic medium becomes more neutral. By measuring how the abundance and brightness of LAEs change with redshift, astronomers can map the progress of reionization, identifying when and where the universe transitioned from opaque to transparent to ultraviolet light. In this way, LAEs act as lighthouses shining through the fog of cosmic dawn, their visibility revealing the state of the space between galaxies as much as the galaxies themselves. Lyman alpha emitter galaxies are typically low in mass and metallicity, but they are not all alike. Some are compact, isolated systems forming stars in relative solitude. Others are found in overdense regions, marking the locations of proto-clusters where galaxies are assembling into larger structures. Extended Lyman alpha blobs, vast clouds of glowing hydrogen tens or even hundreds of thousands of light years across, are sometimes associated with groups of LAEs. These enigmatic structures may be powered by cooling gas accreting onto massive halos, by intense star formation, or by buried active nuclei. Whatever their origin, They reveal that Lyman alpha emission can trace not just galaxies, but the flow of gas on intergalactic scales. If Lyman alpha emitters are defined by what they show, a strong emission line, then Lyman break galaxies are defined by what they hide. A Lyman break galaxy, or LBG, is identified not through a single bright feature, but through a sharp absence of light at wavelengths shorter than the Lyman limit. This break occurs because photons energetic enough to ionize hydrogen are readily absorbed by neutral hydrogen in the galaxy and the intergalactic medium. As a result, a galaxy's spectrum drops abruptly below a certain wavelength, creating a distinctive color signature when observed through multiple filters. By exploiting this effect, astronomers developed the Lyman break selection technique, a powerful method for finding star-forming galaxies at high redshift. The brilliance of the Lyman break technique lies in its simplicity and reach. By comparing images taken through different broadband filters, galaxies that disappear or drop out in bluer bands but remain visible in redder ones can be efficiently identified as high redshift candidates. This method opened the door to systematic studies of galaxies at redshifts of 3, 4, 5, and beyond, long before spectroscopy could reach such faint objects routinely. LBGs quickly emerged as a dominant population of star-forming galaxies in the young universe, revealing that vigorous star formation was widespread at early times. Lyman break galaxies are typically more massive and more dust-rich than classic LAEs, though there is overlap between the populations. Their ultraviolet light traces large populations of young, massive stars, indicating star formation rates far higher than those of most present-day galaxies. Unlike LAEs, whose Lyman alpha emission can be suppressed by dust, LBGs are selected by their continuum emission, making them less sensitive to the complexities of resonance scattering. This difference means that LAEs and LBGs sample complementary aspects of early galaxy populations. LAEs highlight systems with conditions favorable to Lyman alpha escape, while LBGs capture a broader census of star-forming galaxies, including those where dust and gas obscure line emission. The physical properties of Lyman break galaxies reveal a universe in rapid assembly. Their stellar populations are young, often only a few 100 million years old, and their morphologies are irregular and clumpy, reflecting turbulent gas dynamics and ongoing mergers. Many LBGs show evidence of strong galactic winds, inferred from blue shifted absorption lines, indicating that feedback from massive stars is already shaping their evolution. These winds can carry metals into the surrounding medium, contributing to the chemical enrichment of the intergalactic gas and influencing future galaxy formation. Like LAEs, LBGs are deeply entwined with the process of cosmic reorganization. Although they are often observed slightly after the peak of reorganization, their sheer numbers suggest that similar galaxies at earlier times were likely major contributors to the ionizing photon budget. Whether sufficient ionizing radiation escaped from these galaxies to reionize the universe depends on factors such as dust content, gas geometry, and feedback-driven channels, all active areas of research. In this context, LBGs provide the statistical backbone for models of early star formation, while LAEs offer sensitive diagnostics of gas and radiation escape. The relationship between Lyman alpha emitter galaxies and Lyman break galaxies is not one of opposition, but of perspective. Many galaxies likely pass through phases where they would be classified as one or the other, depending on their star formation activity, dust content, and gas dynamics. A young, metal-poor galaxy with strong outflows may shine as an LAE. As it grows more massive and dusty, its Lyman alpha emission may weaken even as its ultraviolet continuum strengthens, shifting it into the LBG category. These classifications are therefore snapshots of evolving systems rather than fixed identities. Together, LAEs and LBGs transformed our understanding of the early universe. They revealed that galaxies were already forming stars vigorously when the universe was a fraction of its current age, that feedback and gas flows were shaping them from the outset, and that the intergalactic medium was intimately linked to galactic activity. One population announces itself through a resonant cry of hydrogen, the other through a sudden silence where light cannot pass. Both are essential voices in the story of cosmic dawn, telling us not only where the first galaxies were, but how their light struggled, scattered, and finally escaped into an expanding universe. Galactic bars are among the most consequential structures a disk galaxy can develop, not because they are visually dramatic, though many are, but because they reorganize motion, redistribute matter, and quietly rewrite a galaxy's future from the inside out. A bar is a long, elongated concentration of stars embedded within the disk, rotating as a coherent structure and extending from the central regions outward for several kiloparsecs. It is not a rigid object, but a dynamical pattern sustained by families of stellar orbits aligned along its length. Once established, a bar becomes a conduit through which angular momentum flows, linking the outer disk, the inner disk, and the galactic nucleus into a single, coupled system. The formation of a bar begins with instability. In a sufficiently cold, massive disk, one where random stellar motions are low compared to ordered rotation, small asymmetries can grow under gravity. As stars respond to these asymmetries, their orbits elongate and align, amplifying the distortion until a bar emerges. Dark matter plays a subtle but critical role in this process. A responsive halo can absorb angular momentum from the disk, allowing the bar to grow stronger and longer over time. In this sense, bars are not merely stellar features, but signatures of an ongoing dialogue between visible matter and the invisible halo that surrounds it. Once a bar forms, its most profound influence is on gas. Gas clouds do not follow the same collisionless orbits as stars. They shock, lose energy, and respond dissipatively to the bar's gravitational torques. Along the leading edges of many bars, dust lanes mark sites where gas is compressed and slowed. From there, the gas flows inward, spiraling toward the central regions. This inward migration can dramatically alter a galaxy's evolution. It can ignite nuclear star formation, build compact central disks or rings, and feed the supermassive black hole at the core. Many galaxies with active nuclei or dense central starbursts show evidence of bars, suggesting a causal link between bar-driven inflow and central activity. Bars also reshape the stellar distribution itself. Over long timescales, they can thicken the central regions, contributing to the formation of boxy or peanut-shaped bulges when viewed edge-on. These structures are not classical bulges formed through mergers, but products of internal, secular evolution, slow rearrangements, driven by the galaxy's own dynamics. In this way, bars demonstrate that galaxies can evolve significantly without external triggers, changing their morphology and internal structure through persistent, self-induced processes. Yet bars are not necessarily permanent. Their strength and longevity depend on gas content, halo properties, and ongoing accretion. In gas-rich disks, the very inflow that a bar induces can weaken it over time by building a massive central concentration that disrupts bar-supporting orbits. Some galaxies may experience multiple bar episodes across their lifetimes, forming, dissolving, and reforming bars as conditions change. The bar, therefore, is best understood not as a fixed feature, but as a phase, a dynamical state that reflects the balance of forces at a given time. If bars govern the radial flow of matter, spiral arms govern its organization across the disk, tracing patterns that are among the most recognizable structures in the universe. Spiral arms are not material features like rigid spokes. They are patterns, regions of enhanced density that rotate through the disk at a different speed than the stars and gas themselves. This concept, known as the density wave theory, resolves a fundamental puzzle. If spiral arms were made of the same stars over time, differential rotation would wind them up tightly and destroy their shape in a few rotations. Instead, the arms persist because they are waves, not objects. Stars and gas flow into and out of them as they orbit the galaxy. In the density wave picture, spiral arms represent quasi-stationary patterns where gravity slightly enhances density along certain azimuthal regions. As gas enters an arm, it slows and compresses, triggering star formation. Massive, short-lived stars form in abundance, illuminating the arm with blue light and ionized gas. As these stars age and drift away from the arm, they fade, leaving behind older populations that no longer trace the pattern. This explains why spiral arms are lined with young stars and nebulae, while older stars are more evenly distributed across the disk. The arm is a catalyst, not a container. The origin of spiral density waves can vary. In some galaxies, they may be self-excited, arising from instabilities within the disk. In others, they may be driven by interactions, tidal forces from companion galaxies that set up long-lived patterns. Bars themselves can generate spiral arms, with the ends of the bar acting as launching points for spiral density waves that propagate outward. In this way, bars and spiral arms are often dynamically linked, parts of a single global pattern of motion and mass redistribution. Not all spiral structure fits neatly into the classic density wave model. Some galaxies exhibit flocculent spirals, patchy, fragmented arms that appear transient and irregular. In these systems, spiral features may arise from local gravitational instabilities and shear, forming and dissolving on relatively short timescales. Others show grand design spirals with two prominent, well-defined arms that extend coherently across the disk, often associated with bars or companions. The diversity of spiral forms reflects the diversity of disk conditions, from gas fraction and stellar velocity dispersion to the influence of environment and halo structure. Spiral arms play a central role in regulating star formation across galactic disks. By concentrating gas, they set the stage for cloud collapse, but they do not guarantee it. Feedback from massive stars, winds, radiation, and supernovae can disrupt clouds and limit star formation efficiency. The result is a self-regulating cycle. Arms gather gas, stars form, feedback disperses clouds, and the interstellar medium flows onward, ready to be compressed again by the next passage through an arm. Over billions of years, this process shapes the disk's stellar population and chemical gradients, enriching inner regions more rapidly than outer ones. The pattern speed of spiral arms, the rate at which the density wave rotates, introduces resonances that further structure the disk. At the corrotation radius, stars and gas orbit at the same angular speed as the pattern, lingering near the arms. Inner and outer Lindblad resonances mark regions where orbital frequencies interact strongly with the pattern, influencing where gas accumulates and where rings or gaps may form. These resonances are not abstract mathematical constructs. They are visible in real galaxies, as rings of star formation, changes in arm pitch angle, or transitions in disk structure. Together, galactic bars and spiral arms reveal that disk galaxies are governed as much by patterns as by particles. They are not static assemblies of stars following isolated paths, but collective systems where gravity organizes motion into large-scale structures that persist through time. Bars channel matter inward, reshaping the center and fueling activity. Spiral arms orchestrate star formation across the disk, setting the rhythm by which gas is turned into stars. One acts along the radius, the other along the azimuth, but both arise from the same fundamental principle: gravity acting in a rotating, self-gravitating disk. In this interplay, a galaxy becomes more than the sum of its stars. It becomes a dynamic system capable of evolving internally, redistributing its own mass and angular momentum, and writing its history into visible structure. Bars and spiral arms are not decorative features painted onto galaxies. They are the mechanisms by which galaxies live, age, and change, shaping their light and matter over cosmic time. Galactic bulges occupy the central regions of disk galaxies, rising above the plane like dense stellar hearts, and for decades they were treated as a single, uniform category. Closer study has revealed that this assumption masked two fundamentally different structures with distinct origins and evolutionary meanings: the classical bulge and the pseudo-bulge. Though they can appear superficially similar in images, their internal properties tell very different stories about how galaxies assemble and transform over time. A classical bulge resembles a small, elliptical galaxy embedded within a disk. It is dominated by old stars, has a roughly spheroidal shape, and is supported primarily by random stellar motions rather than ordered rotation. These bulges are thought to form through violent processes, such as major mergers or rapid early collapse, in which gravitational interactions scramble stellar orbits and funnel material into the center. The resulting structure is dense, dynamically hot, and largely decoupled from the disk's orderly rotation. Classical bulges, therefore, preserve the imprint of early, chaotic phases of galaxy formation, when mergers were more frequent and gas collapsed rapidly in the young universe. Pseudo-bulges, by contrast, are products of patience rather than violence. They form through secular evolution, the slow internal rearrangement of matter driven by structures such as bars and spiral arms. Over billions of years, bars torque gas inward, feeding sustained central star formation and building up a dense central component that still remembers its disk-like origins. Pseudo-bulges tend to be flatter, more rotationally supported, and often contain younger stars, dust, and ongoing star formation. They may show spiral structure, nuclear rings, or boxy and peanut-shaped morphologies when viewed edge-on, features that betray their kinship with the disk rather than with merger-built spheroids. The distinction between classical bulges and pseudo-bulges reframes how astronomers interpret galactic centers. A large bulge no longer automatically signals a violent past. Many massive disk galaxies host prominent central concentrations that are nevertheless pseudo-bulges, grown slowly by internal processes rather than assembled through mergers. This realization has profound implications for models of galaxy evolution, suggesting that quiet, long-term dynamics can rival or even surpass mergers in shaping galactic structure. It also complicates the relationship between bulges and supermassive black holes. While black hole mass correlates tightly with classical bulge properties, the connection appears looser for pseudo-bulges, hinting that black hole growth may be regulated differently in secularly evolving systems. Bulges, whether classical or pseudo, act as memory banks. Their stellar populations, kinematics, and shapes encode information about when and how a galaxy built its central mass. By disentangling these two bulge types, astronomers gain a clearer picture of how galaxies transition from chaotic youth to structured maturity, and how internal dynamics can quietly reshape a system long after the era of major mergers has faded. If bulges record the story of a galaxy's center, thick disk components record the story of its vertical structure and early disk evolution. Most disk galaxies, including the Milky Way, are now understood to consist of at least two stellar disks, a thin disk and a thick disk. The thin disk contains younger stars, gas, and ongoing star formation confined close to the galactic plane. The thick disk, by contrast, is more vertically extended, populated primarily by older stars that orbit above and below the plane with higher random velocities. The thick disk is not merely a puffed-up version of the thin disk. It is a distinct component with its own chemical and kinematic identity. Thick disk stars tend to be older and more metal-poor than thin disk stars, yet they are often enhanced in elements produced by core collapse supernovae, indicating rapid early star formation. This chemical signature suggests that the thick disk formed during an intense, relatively short-lived phase when star formation proceeded quickly, enriching the gas before slower processes took over. The thin disk, in contrast, reflects a more extended and quiescent history, with gradual enrichment over billions of years. How thick disks form remains an active area of research, and multiple pathways may operate simultaneously. One possibility is dynamical heating, in which an initially thin disk is stirred and thickened by minor mergers or interactions with satellite galaxies. Repeated gravitational perturbations can increase stellar velocity dispersion, lifting stars out of the plane and creating a thicker component. Another scenario invokes early turbulent disks, where high gas fractions and intense star formation in the young universe produced disks that were intrinsically thick from the outset. In this view, the thick disk is a fossil of an early epoch when disks were chaotic and gas-rich, while the thin disk formed later as gas settled and turbulence subsided. A third pathway involves radial migration, where stars change their orbital radii through interactions with spiral arms and bars. While migration alone does not thicken a disk significantly, when combined with heating and early turbulence, it can blur the boundaries between components, mixing stars of different origins and complicating the observational picture. The true thick disk in many galaxies may therefore be a composite structure shaped by several processes acting at different times. Thick disks are crucial for understanding the timeline of disk assembly. Their ubiquity across disk galaxies implies that an early turbulent phase is a common feature of galaxy evolution, not an exception. They also provide constraints on the merger histories of galaxies. A very fragile, thin disk would be easily destroyed by frequent mergers. Yet the presence of an old thick disk alongside a long-lived thin disk suggests that galaxies like the Milky Way experienced a limited number of disruptive events after a certain point. In this way, the vertical structure of a disk places limits on how violent a galaxy's later history could have been. They are the largest gravitationally bound structures in the universe, immense cities of galaxies bound together by dark matter and threaded with blazing hot gas. Galaxy clusters are not merely collections of galaxies. They are ecosystems, dynamic, violent, and evolving, where gravity shapes matter on scales measured in millions of light years. A rich cluster may contain hundreds to thousands of galaxies orbiting within a common dark matter halo, their trajectories shaped by a deep gravitational potential that dwarfs any single galaxy. In the heart of such a cluster, the gravitational field is so strong that it can bend light from background galaxies into arcs and rings, revealing its mass through lensing. Yet the visible galaxies are only a small fraction of what is truly there. Most of a cluster's mass resides in dark matter, and most of its ordinary matter exists not in stars, but in a vast reservoir of superheated plasma called the intracluster medium. The intracluster medium is the cluster's true atmosphere, filling the space between galaxies with gas heated to tens of millions of degrees. At such temperatures, the gas emits X-rays, making clusters luminous in high-energy light even when their galaxies appear faint. This plasma holds the chemical fingerprints of billions of years of star formation. Iron, silicon, oxygen, and other heavy elements expelled by supernovae and galactic winds, then trapped by the cluster's gravity. The cluster becomes a chemical archive, preserving the history of element production across cosmic time. Where galaxies show stellar populations, clusters show the grand sum of galactic evolution, pooled into a single gravitational basin. Clusters form through hierarchical growth. In the early universe, small density fluctuations expanded into sheets and filaments of the cosmic web. Galaxies formed in nodes where matter collapsed most strongly. Over time, these nodes drew in smaller halos and merged repeatedly, building up to the largest clusters we see today. Many clusters are still forming now, accreting galaxy groups and smaller clusters along cosmic filaments like a living organism absorbing nutrients. This ongoing growth is not gentle. When clusters collide, they do so at thousands of kilometers per second, driving shock waves through the intracluster medium and heating the gas further. These collisions can trigger starbursts in some galaxies and quench star formation in others, ripping gas from their disks through a process called ram pressure stripping. In a cluster, galaxies are not isolated islands. They are harried and reshaped by their environment. One of the most dramatic features of rich clusters is the presence of a dominant central galaxy, often a giant elliptical, known as a brightest cluster galaxy. These central giants can be among the most massive galaxies in the universe, swollen by repeated mergers and fed by the cluster's gravitational focus. Many host active, supermassive black holes that inflate vast bubbles in the intracluster medium through jets, carving cavities visible in X-rays and preventing the gas from cooling too rapidly. This feedback is crucial. Without it, clusters would suffer runaway cooling flows, funneling gas inward to form stars at rates far greater than observed. Instead, black hole feedback regulates the thermal balance of the cluster, demonstrating, on scales of millions of light years, that a single compact object can influence the fate of entire galaxy ecosystems. Galaxy clusters also stand as pillars of cosmology. Their abundance and distribution across cosmic time depend sensitively on the universe's matter density, the nature of dark energy, and the amplitude of primordial fluctuations. Counting clusters at different redshifts allows astronomers to test cosmological models, measure the growth of structure, and constrain the parameters that govern the expansion of the universe. The Sunyaev-Zeldovich effect, where hot electrons in the intracluster medium distort the cosmic microwave background, allows clusters to be detected across vast distances independent of redshift, making them powerful probes of the universe's large-scale architecture. Yet while clusters are the grand metropolises of the cosmos, most galaxies do not live in such crowded environments. The more typical setting is the galaxy group, a looser, smaller association of galaxies bound together by gravity, often containing just a few large galaxies and dozens of smaller companions. Our own local group is one such structure, dominated by the Milky Way and Andromeda, along with the Triangulum Galaxy and a swarm of dwarf galaxies. Groups are the neighborhood scale of the universe, the environment where galaxies interact frequently enough to matter, but not so violently that everything is stripped bare. Galaxy groups are the crucibles of galactic interaction. Here, galaxy mergers occur more readily than in rich clusters because relative velocities are lower. In clusters, galaxies often pass each other too fast to merge, colliding like ships in a storm, but rarely docking. In groups, however, galaxies can become gravitationally entangled, spiraling together over hundreds of millions of years and merging into larger systems. Many elliptical galaxies likely formed through such mergers in group environments. Groups therefore play a central role in shaping galaxy morphology, transforming spirals into ellipticals and triggering starbursts as gas is compressed during tidal encounters. Groups also possess their own intragroup medium, though typically less hot and less dense than in clusters. This gas, heated to millions of degrees rather than tens of millions, emits in X-rays, but more faintly. It can still strip gas from galaxies, particularly from dwarfs, and can regulate star formation through environmental effects. Yet groups are gentler ecosystems compared to clusters, allowing a wider range of galaxy types and star-forming activity to persist. The evolution from group to cluster is part of the universe's larger growth process. Groups fall into clusters along cosmic filaments, becoming substructures within the cluster's larger halo. Even within clusters, groups can remain identifiable for long periods, orbiting as coherent subunits before tidal forces tear them apart. This nested hierarchy, galaxies in groups, groups in clusters, clusters in superclusters, reflects the fractal-like structure of the cosmic web. Matter in the universe does not arrange itself randomly, but in a patterned architecture shaped by dark matter and gravity. In both clusters and groups, dark matter dominates the mass budget. The visible galaxies are merely luminous traces moving within an invisible gravitational scaffolding. Lensing measurements reveal that dark matter in clusters forms broad, smooth halos, punctuated by subhalos associated with individual galaxies or groups. In collisions like the bullet cluster, the separation between dark matter and hot gas provides compelling evidence that dark matter behaves differently from ordinary matter, passing through the collision relatively unaffected, while gas slows and shocks. Such observations elevate clusters from mere collections of galaxies into fundamental tests of physics. Yet beyond their roles in cosmology and dark matter studies, clusters and groups hold a deeper significance. They reveal that galaxies are not isolated creations. Each galaxy's history is shaped by its environment, its interactions, and its place within the cosmic web. A spiral galaxy in a quiet group may live long, forming stars steadily and nurturing planetary systems for billions of years. A spiral galaxy plunged into a rich cluster may be stripped of gas, its star formation quenched, transformed into a red, dead system dominated by old stars. The environment writes a second biography for every galaxy, beyond what its internal processes would have determined alone. Galaxy clusters are the crowded end state of cosmic assembly, where matter has fallen into the deepest wells and where feedback, shocks, and stripping dominate the lives of galaxies. Galaxy groups are the common social setting of galaxies, where mergers, tidal dances, and slower environmental effects sculpt their evolution. Together, they form the living framework of the universe's structure, an architecture built from gravity, threaded by dark matter, and illuminated by the starlight of billions of galaxies. At the centers of active galaxies, where supermassive black holes feed and flare, structure emerges from chaos in layered, stratified form. The brilliance of an active galactic nucleus is not a single phenomenon, but a complex architecture organized by gravity, radiation, and angular momentum. Closest to the black hole lies the accretion disk, incandescent and turbulent. But beyond it, the environment becomes richer and more intricate. Surrounding this central engine is a system of gas and dust whose geometry determines how an active galaxy appears to the universe. This is the realm of the obscuring torus and the broad and narrow line regions, components that together form the backbone of the unified model of active galactic nuclei. The dusty torus is not a solid donut, but a thick, clumpy distribution of molecular gas and dust arranged roughly in a toroidal geometry around the central black hole and accretion disk. Extending from a fraction of a parsec to several parsecs, it absorbs and reprocesses intense ultraviolet and optical radiation from the inner engine, re-radiating it in the infrared. Its existence explains why some active galaxies appear obscured while others shine openly. When the torus blocks our line of sight to the central regions, the nucleus appears dimmed, reddened, or hidden entirely at optical wavelengths. When we view the system from above or below the torus, the nucleus is revealed in full brilliance. Orientation alone can transform a quasar into a Seyfert galaxy or conceal it behind veils of dust. Within the inner edge of the torus lies the broad line region, a compact zone of fast-moving gas clouds orbiting close to the black hole at thousands of kilometers per second. These clouds are bathed in intense radiation from the accretion disk, causing them to emit broad emission lines whose widths reflect their enormous velocities. Hydrogen, helium, carbon, magnesium, and iron lines appear smeared and widened, carrying within them the gravitational fingerprint of the black hole's mass. By measuring the widths of these lines and the response time of the gas to changes in luminosity, a technique known as reverberation mapping, astronomers can estimate the mass of the central black hole with remarkable accuracy. Further out lies the narrow line region, extending from tens to thousands of parsecs. Here, gas clouds orbit more sedately, their velocities lower, their emission lines narrower and more sharply defined. These regions are often shaped by outflows and ionization cones, where radiation escapes preferentially along the polar axes of the torus. In images, narrow line regions can appear as elongated structures, glowing in forbidden lines of oxygen, nitrogen, and sulfur. They reveal the interaction between the active nucleus and the host galaxy, showing where radiation and winds from the central engine ionize and disturb the surrounding interstellar medium. The interplay between torus, broad-line region, and narrow-line region creates a layered AGN ecosystem. Radiation pressure can puff up the torus. Star formation may occur within its dense clumps. Winds from the accretion disk can erode it over time. The torus itself may not be permanent. It may form and dissipate as accretion rates change, evolving with the life cycle of the active nucleus. In low luminosity systems, the torus may thin or vanish altogether, leaving a naked black hole accreting quietly. In high luminosity quasars, it may be thick and turbulent, shaping the observed spectrum across vast distances. These structures are not merely passive. They regulate how black holes grow and how galaxies evolve. By obscuring radiation, the torus controls how energy couples to the host galaxy. By launching winds and ionization fronts, the broad and narrow line regions participate in feedback processes that can suppress or trigger star formation. In this way, the architecture of an AGN becomes a mediator between the smaller scales of gravity and the largest scales of galactic evolution. Beyond the nuclear regions, the host galaxy itself provides the stage on which this drama unfolds. Among the most graceful and familiar of galactic forms is the spiral galaxy, a structure defined by rotating disks, winding arms, and ongoing star formation. Spiral galaxies are not static pinwheels frozen in space. They are dynamic systems where density waves, gravitational instabilities, and feedback from stars continually reshape the pattern of arms. Their disks are thin and extended, composed of stars, gas, and dust rotating in ordered motion around a central bulge that may host a supermassive black hole. Spiral arms are regions of enhanced density rather than fixed structures. As gas flows through these density waves, it compresses, cools, and collapses to form new stars. Massive, short-lived stars light up the arms with blue-white brilliance, ionizing surrounding gas and creating glowing nebulae. Over time, these stars explode as supernovae, enriching the disk with heavy elements and driving turbulence that regulates future star formation. The arms thus act as stellar nurseries, tracing the ongoing cycle of birth and death that defines spiral galaxies. The structure of a spiral galaxy reflects its mass, environment, and evolutionary history. Some spirals possess prominent central bulges, dense and spheroidal, filled with older stars. Others have smaller bulges or none at all, dominated instead by extended disks. Bars, elongated stellar structures crossing the galactic center, are common and play a crucial role in galactic evolution. By redistributing angular momentum, bars funnel gas inward, feeding central star formation and sometimes fueling active galactic nuclei. In barred spirals, the connection between disk dynamics and nuclear activity becomes especially clear as gas flows along the bar toward the core. Spiral galaxies are rich in cold gas, particularly molecular hydrogen, which fuels star formation. This gas is organized into giant molecular clouds, each capable of forming thousands of stars. The balance between gas inflow, star formation, and feedback determines a spiral galaxy's appearance and longevity. Too much feedback can blow gas out of the disk, quenching star formation. Too little can lead to runaway collapse and starbursts. Spiral galaxies often occupy a middle ground, sustaining star formation at a steady rate over billions of years. The Milky Way itself is a barred spiral galaxy, its arms traced by star-forming regions and dust lanes, its disk rotating serenely around a central bulge. From within, our view is obscured by dust, but observations across radio, infrared, and optical wavelengths reveal the same structures seen in external spirals. Our galaxy's spiral arms host young clusters, massive stars, and nebulae, while its interarm regions contain older stellar populations. At its center lies a supermassive black hole, quiet today, but bearing the scars of past activity, embedded within the same layered AGN structures seen in more active galaxies. Spiral galaxies are sensitive to their environments. In isolation, they can maintain their disks and star formation for long periods. In groups, interactions can trigger bursts of star formation or distort spiral patterns. In clusters, spirals often lose their gas through ram pressure stripping, transforming into lenticular or elliptical galaxies. Thus, the spiral form is not guaranteed. It is a phase in galactic life sustained by rotation, gas supply, and relative isolation. The relationship between AGN structure and spiral galaxies is intimate. Gas, driven inward by spiral arms or bars, can feed the central black hole, igniting nuclear activity. In turn, energy from the AGN can heat or expel gas, influencing star formation in the disk. This feedback loop links scales spanning many orders of magnitude, from the event horizon to spiral arms tens of thousands of light-years away. The torus, broad-line region, and narrow-line region are not isolated curiosities, but components embedded within a living galaxy, shaped by and shaping the spiral structure that surrounds them. Together, the layered anatomy of active galactic nuclei and the elegant form of spiral galaxies illustrate the universe's capacity for organized complexity. Gravity does not merely collapse matter into chaos. It arranges it into disks, arms, tori, and flowing regions of light and gas. From the dusty torus hiding a feeding black hole to the luminous arms birthing new stars, these structures reveal a cosmos where order and violence coexist, where rotation and radiation sculpt matter into forms both beautiful and profound. Bars are among the most influential structures a galaxy can grow, subtle in appearance, yet transformative in effect. A barred spiral galaxy is not merely a spiral with an added feature. It is a system whose internal dynamics have reorganized the flow of matter on galactic scales. In these galaxies, a dense, elongated bar of stars stretches across the central region, cutting through the bulge and connecting directly to the inner spiral arms. This structure rotates as a coherent unit, exerting gravitational torques that profoundly alter the galaxy's evolution. Roughly 2/3 of all spiral galaxies in the local universe, including the Milky Way, possess such bars, suggesting that barred spirals are not exotic exceptions, but a dominant evolutionary state. The formation of a bar arises from instabilities within the galactic disk. As stars orbit within a rotating disk, small asymmetries can grow under gravity, amplified by resonances between stellar orbits and the disk's rotation. Over time, these asymmetries elongate, locking into a bar that redistributes angular momentum across the galaxy. Stars inside the corotation radius lose angular momentum and move inward. Stars outside gain angular momentum and move outward. Gas, being dissipative, responds even more dramatically. It shocks along dust lanes on the leading edges of the bar, losing energy and spiraling toward the galactic center. This inward funneling of gas is the bar's most consequential effect. Bars act as cosmic pipelines, channeling cold molecular gas from the outer disk into the central kiloparsec. There, the gas can ignite intense bursts of star formation, building dense nucleus star clusters or fueling active galactic nuclei. Many Seyfert galaxies, moderately active AGN, are hosted by barred spirals, a connection that underscores the role of bars in feeding central black holes. In some cases, nested bars form, a large-scale bar driving gas inward to a secondary, smaller bar that carries it even closer to the nucleus, bridging the gap between galactic and nuclear scales. Bars also reshape spiral structure itself. The spiral arms of barred galaxies often emerge directly from the ends of the bar, tracing patterns that differ from those in unbarred spirals. These arms may be more open or more tightly wound, depending on the bar's strength and rotation speed. Over billions of years, bars can grow stronger or weaken, dissolve and reform, responding to changes in gas content, dark matter distribution, and dynamical heating of the disk. A galaxy may cycle through barred and unbarred phases multiple times over its lifetime. The presence of a bar accelerates galactic evolution. By driving gas inward, it hastens the consumption of star-forming material in the disk and builds up the central bulge. This process can gradually transform a late-type spiral into an earlier type system with a more prominent bulge and reduced star formation. In this way, barred spirals illustrate how galaxies evolve not only through external interactions, but through internal secular processes, slow, persistent rearrangements driven by gravity and rotation alone. If barred spirals represent galaxies in dynamic self-reorganization, then elliptical galaxies represent the aftermath of cosmic upheaval, systems that have largely exhausted their internal motion and star-forming potential. Elliptical galaxies are smooth, spheroidal, or ellipsoidal collections of stars with little cold gas and minimal ongoing star formation. They range from modest dwarf ellipticals to colossal giant ellipticals containing trillions of stars, often found at the centers of galaxy clusters. Their light profiles are smooth and featureless, lacking the arms, bars, and dust lanes that characterize disk galaxies. Ellipticals are dominated by random stellar motions rather than ordered rotation. Their stars move in 3 dimensions, orbiting in complex, intersecting paths that give the galaxy its rounded appearance. This kinematic structure reflects a violent past. Most elliptical galaxies are thought to form through major mergers, collisions between galaxies of comparable mass. When spiral galaxies merge, their disks are disrupted, their ordered rotations scrambled into random motion. Gas is driven inward, triggering starbursts and feeding central black holes. Over time, feedback from supernovae and AGN expels or heats the remaining gas, shutting down further star formation. What remains is an elliptical galaxy, dynamically hot, gas-poor, and dominated by old stars. The largest ellipticals, often called CD galaxies, sit at the centers of rich clusters. These giants grow not from a single merger, but through repeated accretion of smaller galaxies, cannibalizing their neighbors over billions of years. Their extended stellar halos can stretch hundreds of thousands of light-years, blending seamlessly into the intra-cluster light. Stars stripped from galaxies during encounters and now drifting freely within the cluster's gravitational field. These halos preserve the fossil record of cluster assembly, each layer a memory of past mergers. Elliptical galaxies hosts some of the most massive, supermassive black holes known. The tight correlation between black hole mass and stellar velocity dispersion is strongest in ellipticals, reflecting their shared growth during violent merger events. In these galaxies, AGN feedback has often been decisive, heating gas and preventing it from cooling back into star-forming disks. This feedback locks ellipticals into a passive state where stellar populations age and redden without replenishment. Despite their apparent simplicity, ellipticals are not uniform. Some retain faint shells, ripples, or tidal features, ghostly imprints of past mergers still visible billions of years later. Others show kinematically distinct cores, evidence that their central regions formed through different processes than their outer halos. Even in these seemingly quiet systems, the past is written into the motions of stars and the distribution of light. The contrast between barred spiral and elliptical galaxies illustrates two fundamentally different modes of galactic life. One is rotational, structured, and continually renewing itself through star formation and internal reorganization. The other is dispersion-dominated, quiescent, and shaped by violent encounters that erased prior structure. Yet these forms are not disconnected. Barred spirals can evolve into lenticulars and eventually ellipticals through gas depletion and mergers. Ellipticals can grow further through accretion, their smooth profiles masking a turbulent history. Together, they represent complementary chapters in galactic evolution. Bars show how galaxies change themselves from within. Ellipticals show how galaxies are transformed by collision and collapse. Both are products of gravity acting over immense timescales, sculpting matter into forms that reflect the balance between motion, mass, and energy. In their differences lies the story of how the universe builds complexity, not through a single path, but through many, converging towards structures that endure for billions of years. They occupy the quiet middle ground of galactic evolution, neither actively star-forming spirals nor fully quiescent ellipticals, but something in between, a transitional state frozen in time. Lenticular galaxies, designated S0 in the Hubble sequence, resemble spirals stripped of their defining features. They possess a central bulge and an extended disk, yet lack the sweeping spiral arms, dust lanes, and bright star-forming regions that characterize their spiral cousins. Their disks are smooth and faint, composed largely of older stars, rotating with an ordered motion that hints at a once more vibrant past. Lenticular galaxies are often described as quenched spirals, and this description captures much of their essence. Their stellar populations are typically old and metal-rich, suggesting that star formation shut down long ago. The cold gas reservoirs needed to fuel new stars have either been consumed or removed, leaving behind a stellar structure that preserves the memory of disk rotation without the ongoing renewal of starbirth. In this sense, lenticulars are galaxies caught after transformation but before complete erasure, systems whose architecture still reflects their origins even as their activity has faded. The environments in which lenticular galaxies thrive offer important clues to their formation. They are disproportionately common in galaxy clusters and dense groups where interactions with the surrounding medium are frequent and often destructive. As spiral galaxies fall into clusters, they encounter the hot intracluster medium, a thin but fast-moving plasma that can strip gas from their disks through ram pressure stripping. The galaxy plunges forward, but its gas lags behind, peeled away by the pressure of the surrounding medium. Without gas, star formation grinds to a halt. Over time, spiral arms fade, dust dissipates, and the galaxy settles into a smooth, featureless disk, a lenticular. But gas stripping is not the only path to an S0 galaxy. Tidal interactions and minor mergers can also heat a spiral disk, disrupting spiral structure without fully destroying rotational support. Bars may drive gas inward, feeding central starbursts or active nuclei that exhaust the remaining fuel. Feedback from supernovae or central black holes can further prevent gas from cooling back into the disk. In some cases, lenticular galaxies may even form early as rapidly assembled disks that never acquired or retained enough cold gas to sustain long-term star formation. Thus, the S0 class likely represents multiple evolutionary pathways converging on a similar appearance. Kinematically, lenticular galaxies are revealing. Unlike ellipticals, which are dominated by random stellar motions, lenticulars retain significant rotation in their disks. This rotational support distinguishes them clearly from true spheroidal systems. At the same time, their bulges are often prominent, sometimes rivaling those of ellipticals in mass and density. This combination, rotating disk plus substantial bulge, places lenticulars at a crossroads in galaxy classification. They are not merely faded spirals, nor incomplete ellipticals, but a distinct population reflecting the complexity of galactic transformation. In the broader story of galaxy evolution, lenticular galaxies demonstrate that change does not always require cataclysm. A galaxy can be transformed gently, its star formation quenched not by a single violent merger, but by slow environmental processes that quietly remove its fuel. The result is a galaxy that still turns, still holds its shape, but no longer shines with the light of youth. Lenticulars are the retired spirals of the universe, structurally intact, dynamically ordered, but largely finished with the business of making stars. If lenticular galaxies represent systems whose activity has been muted, then ultra-diffuse galaxies represent something even more enigmatic, galaxies that appear to have almost failed at being galaxies at all. Ultra-diffuse galaxies, or UDGs, are vast in size, yet extraordinarily faint, with stellar densities so low that they verge on invisibility. Some UDGs are as large in diameter as the Milky Way, yet contain only a tiny fraction of its stars. Their surface brightness is so low that they were largely missed by traditional surveys, only coming into prominence in the last decade with the advent of deep, wide-field imaging. At first glance, UDGs seem paradoxical. Galaxies of such large spatial extent should, by conventional wisdom, be massive systems capable of retaining gas and forming stars. Yet UDGs appear ghostly, diffuse, and underluminous, their stars spread thinly across enormous areas. Many reside in rich clusters, like Coma, where the environment is harsh and tidal forces are strong. Others, however, are found in isolation, far from the influence of clusters, suggesting that multiple formation mechanisms must be at play. One leading hypothesis proposes that UDGs are failed giants, galaxies that formed within massive dark matter halos comparable to those of normal spirals, but for reasons not fully understood, converted very little of their baryonic matter into stars. In this scenario, strong feedback from early star formation or active nuclei may have expelled gas before it could collapse efficiently, leaving behind a galaxy dominated by dark matter with only a sparse stellar population. Observations of some UDGs support this idea, revealing surprisingly large numbers of globular clusters, a trait typically associated with massive galaxies rather than dwarfs. Another possibility is that many UDGs are actually inflated dwarfs. In this view, UDGs formed in low-mass halos but experienced processes that puffed up their stellar distributions. Repeated bursts of star formation, followed by supernova feedback, could heat the stellar component, expanding it outward and lowering the surface brightness. Tidal interactions within clusters might further stretch these galaxies, transforming compact dwarfs into diffuse apparitions. This explanation fits well for UDGs in dense environments, where gravitational harassment is common. The diversity of UDG properties suggests that no single origin story suffices. Some UDGs appear dark matter dominated, with velocity dispersions indicating massive halos. Others show little evidence for significant dark matter, challenging fundamental assumptions about galaxy formation. In extreme cases, such as the much-debated galaxy DF2, measurements have suggested an apparent lack of dark matter altogether, though these claims remain controversial. If confirmed, such objects would force a rethinking of the relationship between dark matter and galaxy formation. Ultra-diffuse galaxies also provide a new testing ground for cosmological models. Their abundance in clusters, their spatial distribution, and their internal dynamics place constraints on how dark matter halos form and evolve. If UDGs are common, then galaxy formation must be more inefficient and more varied than previously thought. The existence of large halos with almost no stars suggests that star formation is not an inevitable outcome of halo collapse, but a fragile process sensitive to timing, environment, and feedback. Visually, UDGs are among the most haunting structures in the universe. They appear as pale smudges against the sky, barely distinguishable from the background, their stars scattered thinly like cosmic ash. They challenge observational astronomy, pushing instruments to their limits, and reminding us that much of the universe's structure lies just beyond easy detection. In a sense, UDGs represent the hidden majority, galaxies that exist not in brilliance, but in near silence, contributing mass and structure without spectacle. When considered together, lenticular galaxies and ultra-diffuse galaxies reveal two very different ways a galaxy can become quiet. Lenticulars are structured, orderly, and evolved, systems that once flourished and were later quenched. Ultra-diffuse galaxies are tenuous and elusive, systems that either failed to ignite fully or were stretched and diluted by their environments. One retains the clear imprint of disk rotation and central concentration. The other disperses its stars across vast reaches of space, barely holding itself together. Both, however, underscore a crucial truth. Galaxy evolution is not a single path, but a branching network of possibilities. Some galaxies burn brightly and fade gracefully. Others barely flicker into existence. Some are sculpted by internal dynamics, others by the invisible hand of dark matter and the pressure of their surroundings. Lenticular galaxies show how structure can persist after activity ends. Ultra-diffuse galaxies show how structure itself can be tenuous, fragile, and incomplete. Together, they expand our understanding of what a galaxy can be. Not all galaxies are grand spirals or luminous ellipticals. Some are quiet disks without arms. Some are ghostly spreads of stars, held together by unseen mass. In their subtlety, they remind us that the universe's richness lies not only in its brightest beacons, but also in its faintest forms, waiting patiently to be noticed. They are the small, quiet satellites that haunt the outskirts of larger galaxies, faint enough to be overlooked, yet fundamental to the story of cosmic structure. Dwarf spheroidal galaxies, or DSVs, are among the most dark matter-dominated objects known. They contain little gas, almost no current star formation, and stellar populations that are typically old and metal-poor. Their shapes are diffuse and spheroidal, lacking the organized disks or spiral arms found in larger systems. In visible light, they can appear as barely there smudges, sparse star fields loosely bound, like an ancient ember field scattered across the sky. Yet their dynamical behavior reveals something astonishing. Despite their meager starlight, their gravitational potential is deep, suggesting that most of their mass is invisible. The Milky Way is surrounded by a retinue of dwarf spheroidals: Sculptor, Draco, Ursa Minor, Sextans, Fornax, Carina, Leo III and II, and many more discovered recently through deep sky surveys. These galaxies are crucial laboratories for understanding dark matter because their stars move too fast to be held together by their luminous mass alone. By measuring stellar velocities, astronomers infer large mass-to-light ratios, sometimes hundreds or even thousands, implying that DSVHs may be embedded in massive dark matter halos. In cosmological theory, such halos are the building blocks of larger structures, and dwarf spheroidals are living fossils of that process, small halos that survived, orbiting a larger galaxy that did not fully consume them. Their histories are written in their stars. Many dwarf spheroidals show extended star formation histories with multiple stellar populations, each with distinct chemical signatures. Some formed stars early and then quenched quickly, perhaps due to reionization heating the intergalactic medium and preventing fresh gas from cooling into small halos. Others formed stars intermittently over billions of years, with bursts separated by long, quiet periods. Chemical abundance patterns in their stars preserve evidence of the first supernovae and the earliest enrichment processes. In some cases, the abundance ratios suggest that a small number of supernova events dominated their chemical evolution, making DESPs a window into nucleosynthesis in low metallicity environments. Yet dwarf spheroidals are fragile. Their lack of gas suggests they have been stripped or starved. Orbiting within the gravitational influence of a larger galaxy, they are subject to tidal forces that can stretch and distort them. Some show hints of tidal tails, elongated shapes, or velocity gradients that suggest ongoing disruption. Their gas may have been removed by ram pressure stripping as they pass through the hot halo of their host galaxy, or blown out by early supernova feedback when their shallow potentials could not retain heated gas. Over time, the combination of environmental stripping and internal feedback can turn a small, gas-rich system into a gas-poor DSVH, fading, cooling, and drifting towards silence. Dwarf spheroidals also lie at the center of one of the most important tensions in modern cosmology. In LCDM simulations, dark matter halos form hierarchically, predicting many more small subhalos around galaxies like the Milky Way than the number of luminous satellite galaxies observed. This is the missing satellites problem, and dwarf spheroidals are the visible tip of a much larger predicted population. One resolution is that many small halos never formed stars, remaining dark. Another is that feedback and reionization suppressed star formation in low-mass halos leaving only a few survivors as luminous dwarfs. Dwarf spheroidals are therefore not merely small galaxies, they are test cases for the relationship between dark matter halos and luminous matter, and for whether our cosmological model correctly predicts the small-scale structure of the universe. If dwarf spheroidals are the quiet, gas-poor relics, then dwarf irregular galaxies, or DIRs, are their lively counterparts, small galaxies still rich in gas, still forming stars, still shaped by turbulence rather than order. Dwarf irregulars lack the smooth symmetry of ellipticals and the organized disk patterns of spirals. They are patchy, chaotic systems, their starlight concentrated in clumps of star formation and scattered associations. They often appear lopsided or asymmetrical, shaped by feedback from supernovae, by the stochastic nature of star formation in small systems, and sometimes by interactions with neighbors. Dwarf irregulars are typically found in lower density environments, the outskirts of groups, the fringes of clusters, or in relative isolation. This makes sense because their defining feature, their abundant cold gas, is easily removed in dense environments. In the calm of the field, gas can persist, cooling into molecular clouds and fueling star formation. In such settings, dwarf irregulars can continue forming stars for billions of years, slowly building their stellar mass in intermittent bursts. Their metallicities tend to be low because their star formation rates are modest, and because outflows can carry away freshly enriched material. The life of a dwarf irregular is governed by feedback. In a large spiral galaxy, a supernova may carve a bubble in the interstellar medium but rarely threatens the entire galaxy's gas reservoir. In a dwarf irregular, however, the gravitational potential is shallow enough that clustered supernovae can drive large-scale outflows, venting gas into the surrounding medium. This does not necessarily quench the galaxy permanently. Often, the gas remains bound in an extended halo or reaccretes over time, but it can regulate star formation into a stop-and-start rhythm. The galaxy becomes a breathing system, contracting and cooling into star formation, then heating and expanding under feedback, then cooling again. Many dwarf irregulars show complex gas structures, expanding shells, supershells, filaments, and holes carved by stellar winds and supernova blasts. In the large and small Magellanic Clouds, which are close enough for detailed study, such structures are ubiquitous. Star formation propagates through these systems like a chain reaction, with supernova-triggered compression igniting new star-forming regions at the edges of expanding bubbles. In this way, dwarf irregulars reveal star formation in its most direct and raw form, less smoothed by large-scale galactic dynamics and more shaped by local physics. Dwarf irregulars are also important in the cosmic assembly story. In hierarchical models, large galaxies grow partly by accreting dwarfs. Many dwarf irregulars may eventually fall into larger galaxies and be transformed, stripped of gas, tidally heated, and converted into dwarf spheroidals. This transformation pathway, sometimes called morphological quenching by environment, provides a natural link between the two classes. A gas-rich, star-forming DIR entering a larger galaxy's halo may lose its gas through ram pressure, stop forming stars, and fade into a DSVH. The local group offers evidence of this environmental gradient. Gas-rich dwarf irregulars tend to lie farther from the Milky Way and Andromeda, while gas-poor dwarf spheroidals cluster closer in. Yet not all dwarf spheroidals necessarily began as dwarf irregulars. Some may have formed early and quenched due to reorganization, never sustaining long-term star formation. Others may have been stripped remnants of more massive systems. The diversity of dwarf galaxies mirrors the diversity of the processes shaping them. Together, dwarf spheroidals and dwarf irregulars illustrate the smaller scales of galactic existence, where gravity, gas physics, and environment compete in delicate balance. The DSPH is a whisper of starlight held together by dark matter, a system whose visible component is almost an afterthought compared to its invisible mass. The DIR is a living, breathing system of gas and feedback, chaotic yet productive, forming stars in bursts, as if the galaxy itself hesitates between growth and disruption. One is the relic, the other the workshop. In their differences lies a broader lesson. Galaxies are not defined only by mass or shape, but by their ability to hold on to gas and sustain star formation. On the smallest scales, that ability can be lost easily, stripped away by environment or blown out by feedback. Dwarf galaxies reveal how fragile galactic life can be, and how deeply the universe's structure depends on the unseen scaffolding of dark matter, without which these faint systems would dissolve into the void. There are galaxies that form stars as a steady background rhythm, and then there are galaxies that erupt, systems that, for a brief and violent span of cosmic time, burn through their gas as if the universe has struck a match at their core. A starburst galaxy is defined by this intensity, a galaxy undergoing star formation at a rate so high that if sustained, it would exhaust its available cold gas in a fraction of a typical galaxy's lifetime. Starbursts are not merely active galaxies, they are galaxies in an accelerated state of creation, converting raw interstellar material into stars with a ferocity that can remake their structure and chemistry in a single episode. Starburst activity can be triggered by several pathways, but the most dramatic involve interactions, close encounters, and mergers that gravitationally torque gas inward. When galaxies pass near each other, tidal forces stretch their disks, drive bars and instabilities, and funnel gas toward their central regions. There, the gas compresses, cools, and collapses into dense molecular clouds, igniting runaway star formation. In major mergers, two spirals can collide and transform into a single disturbed system, with gigantic central starbursts, their cores packed with dust, superstar clusters, and intense infrared luminosity. These are the luminous infrared galaxies and ultraluminous infrared galaxies, objects so dust-enshrouded that much of their power emerges not in visible light, but in the infrared, where heated dust radiates the energy of newly formed stars. But starbursts can also be driven internally, especially in gas-rich galaxies where disk instabilities produce giant clumps and rapid star formation without an external trigger. In the early universe, when galaxies were more gas-rich and the cosmic accretion of fresh material was stronger, starbursts may have been far more common. Indeed, many high redshift galaxies show clumpy star formation and turbulent disks, suggesting that normal star formation in the young universe was already closer to starburst-like conditions compared with the calmer present-day Milky Way. The signature of a starburst is multifaceted. In optical and ultraviolet light, massive young stars dominate, producing blue continua and strong emission lines. In infrared, dust warmed by intense radiation glows brightly, often outshining the galaxy's visible output. In radio, synchrotron emission rises as supernova rates surge, filling the galaxy with relativistic particles. Starbursts are also factories of supernovae. Because massive stars form in abundance, they die quickly, detonating within a few million years. The resulting supernova feedback can carve bubbles and superbubbles in the interstellar medium, drive turbulence, and launch outflows that vent gas into the halo or even beyond. These outflows are among the most important consequences of starbursts. When many supernovae occur in clustered regions, their combined energy can drive galactic winds, powerful streams of hot gas, and entrained cold material that escape the disk. These winds carry metals, oxygen, carbon, iron, silicon into the circumgalactic medium and intergalactic space, enriching the universe with heavy elements. In this way, starbursts help explain why the intergalactic medium contains metals far from galaxies. They are the cosmic bellows that blow the products of stellar alchemy outward, spreading the chemical ingredients needed for future generations of stars and planets. Yet starbursts are also self-limiting. The same feedback that drives winds can disrupt molecular clouds, halt collapse, and suppress further star formation. Radiation pressure, stellar winds, and supernova shocks can heat and expel gas, eventually starving the starburst of fuel. Thus, starbursts tend to be transient, intense episodes lasting tens to hundreds of millions of years, after which the galaxy may return to a quieter state or evolve into something new. In merger-driven starbursts, the aftermath can be transformative. The violent mixing of stellar orbits can erase a disk and create an elliptical or lenticular remnant, while the central black hole, fed by the same inflows that fueled the starburst, may ignite as an active galactic nucleus and further suppress star formation. Starbursts, therefore, sit at the junction of multiple evolutionary pathways, acting as engines of rapid growth and rapid change. If starburst galaxies represent the universe's most intense stellar manufacturing zones on large scales, then green pea galaxies represent that intensity concentrated into small, compact bodies, tiny, bright systems whose properties evoke conditions more typical of the early universe than of the present day. Green pea galaxies were discovered in the late 2000s through citizen science classification of Sloan Digital Sky Survey images. They appeared as small, round, greenish dots, peas, because their visible light was dominated by strong emission in the Aphy line, which falls into the green portion of the SDSS color filters. What seemed like an optical oddity soon revealed itself as an astrophysical treasure, a local population of compact galaxies undergoing extreme star formation with unusually high ionization and low metallicity. Green pea galaxies are typically only a few kiloparsecs in size, far smaller than the Milky Way. Yet their star formation rates relative to their mass can be extraordinary. They are dense star-forming knots, often with properties resembling high redshift galaxies from the epoch of reorganization, systems that once flooded the early universe with ionizing radiation. This resemblance is what makes green peas so valuable. They provide nearby laboratories for studying conditions that were otherwise accessible only at vast distances and in the deep past. Their spectra are distinctive, strong, narrow emission lines, especially Aphy, along with strong hydrogen recombination lines and often elevated ratios indicating hard ionizing radiation fields. Many show low dust content and low metallicities, implying relatively chemically young systems or systems that have lost metals through outflows. Their star-forming regions can be dominated by extremely hot, massive stars and dense heterogeneous regions where gas is fully ionized. In some cases, these galaxies may host populations of very young star clusters whose combined radiation resembles the energetic outputs expected from early universe star formation. One of the most significant questions surrounding green pea galaxies is whether they can leak Lyman continuum photons, ionizing ultraviolet radiation capable of stripping electrons from hydrogen atoms. In the early universe, such photons are believed to have driven cosmic reorganization, transforming the neutral intergalactic medium into the ionized universe we see today. Direct observation of Lyman continuum escape is difficult, but some green peas appear to be among the best local candidates. Their compactness, strong ionization, and sometimes porous interstellar media suggests that radiation may escape through low-density channels carved by feedback. If so, green peas may represent living analogues of the galaxies that reorganize the cosmos. Green pea galaxies also illustrate the role of bursts and feedback in small systems. Like dwarf irregulars, they may experience episodic star formation, but at far higher intensities. Their compactness makes feedback especially potent. Supernovae and winds can rapidly disrupt gas, potentially leading to outflows that regulate future star formation and shape the galaxy's evolution. In extreme cases, these feedback-driven processes may produce galaxies that flare briefly into brilliance and then fade, contributing to the population of faint dwarfs and low-surface brightness systems later on. Starburst galaxies and green pea galaxies thus represent two scales of the same underlying phenomenon: star formation pushed to an extreme. The starburst galaxy may be a massive system, often merger-driven, whose entire central region becomes a furnace of stellar creation. The green pea galaxy is a compact, chemically young, high ionization system whose star formation is intense enough to make it a local stand-in for the early universe. One demonstrates how interactions can ignite galaxy-wide transformation. The other demonstrates how small galaxies can reach conditions so energetic that they approach the physics of cosmic dawn. Together, they show that star formation is not a uniform process. It can accelerate into bursts that sculpt galaxies, enrich intergalactic space, and perhaps even alter the ionization state of the universe itself. In the roar of starbursts and the bright, compact blaze of green peas, the cosmos reveals one of its most fundamental powers: the ability to concentrate gas, ignite new suns in vast numbers, and reshape the future through brief episodes of extraordinary creation. Tidal dwarf galaxies are born not in the quiet, gradual condensation of primordial gas inside a dark matter halo, but in the violent artistry of collision. Small galaxies assembled from the torn-out flesh of larger ones. When two massive galaxies pass close enough to distort each other gravitationally, their disks can be pulled into long tidal tails, luminous streamers of stars, gas, and dust, flung outward like ribbons. These tails are not just debris fields, they are dynamic structures where gravity can gather material into knots dense enough to collapse, cool, and ignite star formation. Out of this chaos, a new kind of galaxy can emerge, a dwarf galaxy formed from recycled material, assembled in the wake of a merger rather than in isolation. The idea is both elegant and unsettling because it challenges the usual hierarchy of galaxy formation. In the standard cosmological picture, most galaxies form inside dark matter halos, gravity wells created by invisible mass that draws in gas and allows stars to form. Tidal dwarf galaxies, however, are expected to form primarily from baryonic material, torn from the disks of interacting galaxies. The matter that becomes the tidal dwarf is already chemically enriched, already processed by previous generations of stars, already laced with metals and dust. This gives tidal dwarfs a distinct fingerprint. Compared to primordial dwarfs of similar mass, they can show higher metallicities because their gas was not pristine, but inherited from the outer disks of larger galaxies. In a sense, tidal dwarfs are second-generation galaxies, assembled from pre-enriched ingredients, like a new city built from the bricks of an older one. In many interacting systems, the tidal tails display bright clumps, star-forming condensations where gas has pooled and collapsed. Some of these clumps are transient, dispersing as the tidal tail evolves. Others may become self-gravitating enough to detach and survive as independent galaxies. Their survival depends on many factors: the mass and density of the clump, the orbit it inherits, the gravitational field of the parent system, and how strongly feedback from its own young stars disrupts its gas. If the clump is dense enough, it can resist tidal shearing and remain coherent. If it forms stars too violently, supernova feedback may blow out its gas and weaken its binding. The birth of a tidal dwarf is therefore a delicate contest between gravitational assembly and energetic disruption, played out in the aftermath of cosmic violence. One of the most intriguing aspects of tidal dwarf galaxies is the question of dark matter. If they truly form from disk material, then they should contain relatively little dark matter compared to dwarfs formed in their own halos, because the tidal material primarily originates from the brine-rich disk rather than the dark matter-dominated halo. This would make tidal dwarfs unusually light in dark matter, altering their internal dynamics and rotation curves. Yet measuring this is difficult because small galaxies are messy, star-forming, and affected by their environments. Still, the possibility is profound. If tidal dwarfs exist as long-lived systems with low dark matter content, they become natural experiments testing the relationship between visible mass and gravity, and they complicate the use of dwarf galaxies as straightforward dark matter traces in cosmology. Tidal dwarfs also matter because galaxy mergers were more common in the early universe. If interactions and mergers were frequent, then the formation of tidal dwarfs may have been more common too, potentially contributing a population of dwarfs that do not fit the simple halo-based origin story. Some of today's dwarf galaxies, in groups and clusters, might, in principle, be the long-lived descendants of ancient tidal dwarfs, their origins disguised by time. Their relatively high metallicities for their mass, their association with past merger remnants, and their locations along tidal debris fields can provide clues, but the longer the time since formation, the harder it becomes to prove ancestry. This uncertainty gives tidal dwarfs a kind of haunting quality in galactic archaeology. They may be more common than we recognize, hidden in plain sight among the vast dwarf populations around larger galaxies. Yet in the grand narrative of morphology, tidal dwarfs are only one of the strange shapes galaxies can take after disturbance. Sometimes a collision does not merely fling out tails and birth small recycled companions. Sometimes it punches a wave through a disk and leaves behind one of the most visually dramatic structures in all of astronomy: a ring galaxy. A ring galaxy looks like a cosmic target, a bright, circular ring of star formation surrounding a relatively empty-looking center, often with spokes or arcs of light. Among them, the Cartwheel galaxy stands as an archetype, a breathtaking example of how a single encounter can reorganize a galaxy's gas and star formation into a near-perfect circle. Ring galaxies are typically formed through a specific kind of interaction, a head-on or near head-on collision, in which a smaller galaxy plunges through the disk of a larger one. This is not a gentle pass-by. The intruder drives a gravitational disturbance through the disk like a stone dropped into a pond. The disk responds by sending a radially propagating density wave outward. As this wave moves through the gas-rich disk, it compresses gas along its leading edge, triggering a moving front of star formation. The result is a bright ring of young stars, H2 regions, and glowing gas that expands outward over tens or hundreds of millions of years. The ring is not a static structure. It is a traveling shock of density and starbirth, a wave that marks the disk's response to a sudden gravitational impulse. The central region of many ring galaxies appears dim, not because it is empty, but because much of the gas has been swept outward into the ring, leaving behind older stars and less active star formation in the interior. In some cases, a nucleus remains, sometimes offset from the center if the collision was not perfectly symmetric. In others, the core may be faint, disrupted, or partially dispersed, depending on the violence and geometry of the encounter. The ring itself can be extraordinarily luminous in ultraviolet and blue light, dominated by massive stars that will live only a few million years before exploding. In the infrared, dust heated by these star-forming regions glows strongly, and in radio wavelengths, synchrotron emission rises as supernovae begin to populate the ring with relativistic particles. A ring galaxy, therefore, is not just a shape, it is a timeline, a record of when and where star formation has been triggered as the wave moved outward. The Cartwheel class is particularly spectacular because it often shows secondary rings and spoke-like features linking the core to the outer ring. These spokes may arise from gravitational instabilities and the dynamics of the disk as it is stretched and rearranged, or from streams of material responding to the impulse and the evolving potential. Whatever their precise origin, they add to the impression that the galaxy has been briefly reorganized into a patterned architecture of shock, compression, and flow. In a sense, a ring galaxy is a galaxy caught mid-reaction, as if the collision has made its internal physics visible. Ring galaxies also illuminate the relationship between dynamics and star formation. They demonstrate that star formation is not merely a local process inside clouds, but can be orchestrated on galactic scales by global gravitational events. A ring wave can trigger star formation more efficiently than the galaxy's prior spiral arm pattern, concentrating gas into an expanding boundary where collapse becomes inevitable. The ring becomes a moving factory line, creating clusters and associations in sequence as it travels. This sequential star formation allows astronomers to estimate the ring's expansion speed and reconstruct the timing of the collision. By mapping stellar ages across the ring and interior, one can read the history of the event like tree rings, each zone representing a different stage of the wave's passage. Like tidal dwarfs, ring galaxies are transient in the long view. The ring wave eventually dissipates. Gas consumption and feedback reduce its intensity. The disk relaxes into a new equilibrium. The galaxy may later rebuild spiral structure, fade into a lenticular form, or merge further, depending on its environment and subsequent end encounters. Yet even after the bright ring fades, the galaxy can retain scars, warped disks, disturbed kinematics, or redistributed gas reservoirs that alter its evolution for billions of years. Taken together, tidal dwarf galaxies and ring galaxies reveal two complementary outcomes of galactic interaction. In one, the outskirts are torn into tails, and from those tails, new dwarf systems may condense. Small galaxies born from the recycled material of larger ones, carrying enriched chemistry and a potentially unusual relationship to dark matter. In the other, the disk itself responds like a resonant instrument struck by an intruder, sending an expanding wave that reshapes star formation into a luminous circle. One outcome creates new, independent structures on the periphery. The other reorganizes the existing disk into a temporary but iconic geometry. Both remind us that galaxies are not fixed forms, but responsive, living systems shaped by gravity's sudden gestures. Collisions do not simply destroy, they create, repattern, and redistribute. They can build a dwarf out of a tail and draw a ring out of a disk. And in doing so, they reveal something profound about the universe's architecture, that even on the grandest scales, structure can arise from disturbance, and beauty can be the visible signature of a violent encounter that happened millions of years ago, still echoing in light. Polar ring galaxies look like cosmic paradoxes, systems in which a galaxy carries a second, nearly perpendicular structure like a luminous halo band, as if a disk has been fastened around it at a right angle. They are among the most visually arresting and dynamically informative galaxies known because they expose, in a single object, the history of gravitational capture and the hidden geometry of dark matter. At their core is usually an early-type host, often lenticular-like or elliptical-like in appearance, surrounded by a ring or disk of gas, dust, and stars orbiting in a plane nearly orthogonal to the host's main stellar body. The effect is a cross-shaped architecture in 3 dimensions, one component rotating one way, another rotating around a different axis entirely, both held together by a common gravitational potential. The very existence of a polar ring implies a past event of acquisition. A galaxy does not normally grow 2 large, stable angular momentum axes through quiet, isolated evolution. Something must have arrived from outside. Gas captured from a passing neighbor, a smaller galaxy tidally stripped and absorbed, or a minor merger that delivered material with a dramatically different orbital orientation. In one formation pathway, a gas-rich dwarf galaxy is disrupted during a close encounter. Its gas stretched and then wrapped into a polar orbit around the host, gradually settling into a coherent ring. In another, the host accretes cold gas directly from the surrounding cosmic web along a filament misaligned with the host's existing rotation, creating a polar structure that slowly forms stars and becomes visible. Each pathway leaves a polar ring as a fossil of angular momentum, a preserved record of how matter arrived. These rings are not mere decorative features. Because they are made of gas and young stars, polar rings are often sites of active star formation, bright with H2 regions and dust lanes. The ring can contain a significant fraction of the system's total gas mass, and in some cases, the ring's stellar mass is substantial. The host galaxy, by contrast, may be relatively quiescent, its central body dominated by older stars. This contrast creates a striking juxtaposition. An older, smoother core with a youthful, star-forming structure in a different plane, like a relic galaxy wearing a fresh, newly formed belt of light. The dynamical value of polar ring galaxies is immense because they provide a rare opportunity to probe the shape of the dark matter halo in 3 dimensions. In a normal disk galaxy, most traces of motion lie in the disk plane, meaning rotation curves reveal the radial mass distribution, but not the halo's three-dimensional shape. In a polar ring system, the host and the ring orbit in nearly perpendicular planes, allowing astronomers to measure the gravitational potential along two axes. If the halo is spherical, the ring and host dynamics align with one set of predictions. If the halo is flattened or triaxial, the precession and stability of the ring reveal that geometry. In this way, polar ring galaxies become natural laboratories for testing dark matter halo shapes, information that is otherwise frustratingly difficult to extract. Stability is the key. A polar ring cannot persist long if the host's gravitational potential is highly asymmetric in a way that torques the ring strongly. Such torques would cause the ring to precess and warp, potentially dissolving it over time. The fact that many polar rings appear coherent suggests that, in those systems, the halo and baryonic mass distribution allow a relatively stable polar orbit. This implies constraints on halo flattening and alignment that are crucial for models of galaxy formation. Thus, what looks like an oddity is actually a precise instrument, a structure that survives only if the underlying gravitational architecture permits it. Polar ring galaxies also reveal how galaxies can grow in unexpected ways. Instead of adding material along the plane of the main disk, they demonstrate that galaxies can accrete matter with dramatically different angular momentum, building multi-spin systems. This has broader implications for galaxy evolution because the cosmic web delivers gas along filaments that can change orientation over time. If a galaxy's accretion direction shifts, it may develop misaligned disks, warps, or in rare cases, a full polar ring. The polar ring, therefore, is an extreme but illuminating case of a more general truth. Galaxies are open systems, continually shaped by what they capture. If polar ring galaxies are defined by geometry and history, low surface brightness galaxies are defined by absence, by what they do not show. An LSB galaxy is not necessarily small or faint in total. It is faint per unit area, its starlight spread thinly across a wide disk. The defining trait is low surface brightness, typically lower than the night sky background in optical wavelengths, which makes these galaxies difficult to detect. For much of the 20th century, they were undercounted because they simply did not stand out in photographic surveys. Only with deeper imaging and modern digital surveys did their true abundance become clear, revealing that a substantial fraction of galaxies in the universe may be LSB systems. LSB galaxies often look like spirals with their lights turned down. They can possess disks, sometimes with spiral structure, but the arms are faint and the stellar density low. Some are giant, massive extended disks with sizes comparable to large spirals, but with far fewer stars per square kiloparsec. Others are small and diffuse, overlapping in appearance with ultra-diffuse galaxies, though the categories are not identical. What unites them is that star formation has been inefficient. Their gas is often present, sometimes abundant, yet it remains in low-density conditions that do not trigger strong star formation. The galaxy has the raw material but lacks the compression, instability, or environmental triggers to convert that material into dense molecular clouds. One of the key reasons LSB galaxies are so fascinating is their relationship to dark matter. Many appear to be strongly dark matter dominated, with rotation curves indicating that dark matter shapes their dynamics even in their inner regions. In high surface brightness spirals, The stellar disk often contributes significantly to the inner rotation curve. In LSB galaxies, the stellar contribution is small, and the rotation curve can rise slowly, reflecting a diffuse mass distribution. This has made LSB galaxies central to debates about dark matter profiles. Some observations suggest cored dark matter halos, flat central density distributions, rather than the steep cusps predicted by certain simulations. Whether this is due to baryonic feedback reshaping halos or points to new dark matter physics has been a long-running question, and LSB galaxies sit at the heart of it because their baryonic influence is minimal, making them cleaner tests of dark matter structure. Their inefficiency in forming stars can arise from multiple factors. Their gas surface densities may sit below the threshold needed for widespread gravitational collapse, so star formation occurs only in small pockets. Their disks may be dynamically stable, with low shear and low perturbations, preventing spiral density waves from compressing gas. Their environments may be quiet, lacking interactions that would trigger bursts. Some may have high angular momentum halos, causing gas to settle into broad, diffuse disks rather than compact, star-forming ones. This high angular momentum scenario is particularly compelling. If the dark matter halo spins more rapidly, the baryons inherit that angular momentum, spreading out and lowering density, which suppresses star formation. The result is a galaxy that remains gas-rich but star-poor, rotating serenely without ever igniting into brilliance. LSB galaxies also challenge our intuition about what a typical galaxy is. If many galaxies are low surface brightness, then the luminous spirals that dominate textbook images may be only the easily visible minority. The universe may be populated by vast numbers of dim disks whose total mass and extent matter for cosmic structure, but whose light barely registers in conventional surveys. This has implications for the baryon census, the distribution of angular momentum, and the statistical properties of galaxy formation. LSB galaxies force astronomers to confront selection effects. What we see most easily is not necessarily what is most common. There is a thematic link between polar ring galaxies and LSB galaxies that runs deeper than appearance. Both are reminders that galaxy evolution is not a single, tidy sequence. Polar rings reveal that galaxies can acquire matter from unexpected directions, building stable structures that expose the shape of the invisible halo. LSB galaxies reveal that galaxies can evolve in slow, inefficient modes, forming extended disks without strong star formation, leaving dark matter as the dominant shaper of their dynamics. One is defined by dramatic geometry, the other by understated light. Yet both serve as probes of dark matter, polar rings through multiplane dynamics, LSB galaxies through baryon-pore rotation curves, and both preserve the memory of how matter moved into and through a galaxy over cosmic time. In the end, these classes broaden the vocabulary of galactic form. A galaxy can be crossed by a ring that orbits at right angles, a living relic of capture and alignment. A galaxy can be so diffuse in light that it hides in the sky's background, an extended disk shaped by angular momentum and dark matter more than by starlight. Together, polar ring galaxies and low surface brightness galaxies reveal a universe where the invisible often governs the visible, and where the strangest structures are not mere curiosities, but keys to understanding the deep architecture of gravity itself. At the hearts of many galaxies lies a phenomenon so energetic that it can rival or outshine the combined light of all the stars around it. A compact engine capable of reshaping not only its host galaxy, but the surrounding cosmic environment as well. An active galactic nucleus, or AGN, is not a single object, but a state, a phase in a galaxy's life when its central supermassive black hole is actively accreting matter. As gas, dust, and stars wander too close to this gravitational abyss, they are torn apart and flattened into a rotating accretion disk. Friction, turbulence, and magnetic stresses within the disk heat the infalling material to extreme temperatures, converting gravitational energy into radiation across the electromagnetic spectrum. The result is an intense, compact source of light and power emerging from a region no larger than the solar system, yet visible across billions of light years. AGN come in many observational guises: quasars, Seyfert galaxies, blazars, radio galaxies, but these varieties are now understood as different manifestations of the same underlying engine. The diversity arises from orientation, accretion rate, and environment rather than from fundamentally different processes. In some systems, our line of sight peers directly into the bright inner regions, revealing broad emission lines and blinding luminosity. In others, dusty structures obscure the core, hiding the central engine behind veils that absorb and re-radiate its energy. In still others, relativistic jets point almost directly at Earth, boosting their emission through relativistic beaming and creating the most violently variable sources known. The AGN unification picture weaves these appearances together into a coherent framework, where geometry and perspective determine what we see. At the center of this framework is the black hole itself, with masses ranging from millions to billions of times that of the Sun. Yet the black hole alone is not enough. An inactive supermassive black hole is effectively invisible. What makes an AGN active is the supply of fuel and the conditions that allow matter to spiral inward efficiently. Gas inflows can be driven by galaxy mergers, close encounters, bars in spiral galaxies, or instabilities within the disk. When sufficient material reaches the central parsecs, the accretion disk lights up and the galaxy enters an active phase. These phases are episodic, lasting millions to tens of millions of years, brief flashes in a galaxy's multi-billion-year history. The influence of an AGN extends far beyond its luminous core. Radiation pressure, winds, and jets can inject enormous energy into the surrounding interstellar medium. This feedback can heat or expel gas, suppressing star formation and regulating the growth of the galaxy. In some cases, feedback may also compress gas and trigger star formation, depending on geometry and timing. This delicate balance links black hole growth to galaxy evolution, explaining why black hole mass correlates so strongly with the properties of the galactic bulge. The AGN is not merely a passenger in the galaxy, it is a co-architect of the galaxy's fate. Among the most dramatic expressions of AGN activity are radio galaxies, systems in which a significant fraction of the black hole's power is channeled into relativistic jets that shine brightly at radio wavelengths. These jets are narrow, collimated streams of plasma launched from the vicinity of the black hole and accelerated to near the speed of light by magnetic fields twisted by the rotating disk and black hole. They pierce through the host galaxy and extend far into intergalactic space, sometimes reaching lengths of millions of light years. Where the jets interact with surrounding gas, they inflate lobes of radio-emitting plasma, creating structures that dwarf the galaxy itself. Radio galaxies are traditionally divided into two main morphological classes, known as FRY and FRE2, after the astronomers who first identified the distinction. The difference lies not in the black hole itself, but in how the jet propagates and dissipates its energy. FRI radio galaxies show jets that are brightest near the core and fade with distance. Their jets tend to decelerate relatively quickly, interacting strongly with the surrounding medium and becoming turbulent. The radio emission is concentrated toward the center, and the outer regions appear diffuse and less sharply defined. These systems are often found in massive elliptical galaxies at the centers of clusters, where the dense intra-cluster medium can slow and disrupt the jets. FR2 radio galaxies, by contrast, are among the most spectacular structures in the universe. Their jets remain highly collimated over enormous distances and terminate in bright hotspots where they slam into the intergalactic medium. These hotspots are sites of intense particle acceleration, producing strong radio emission. The lobes beyond them glow brightly, often symmetrically arranged on opposite sides of the host galaxy. In FR2 systems, the bulk of the radio power resides far from the core, marking the points where the jets deposit their energy most violently. These galaxies often host some of the most powerful AGN known, capable of injecting vast amounts of energy into their environments. The distinction between FRI and FR2 radio galaxies reflects a complex interplay between jet power and environment. More powerful jets can punch through surrounding gas without decelerating, producing FR2 morphologies. Less powerful jets may be disrupted by interaction with the ambient medium, producing FR1 structures. Host galaxy mass, black hole spin, accretion mode, and the density of the surrounding gas all play roles. In this sense, the FRI-FR2 dichotomy is not a simple binary, but a continuum shaped by physical conditions. Some systems show hybrid features, with one jet behaving like an FRY and the other like an FR2, highlighting the sensitivity of jet evolution to local circumstances. Radio galaxies are not merely exotic curiosities. They are agents of cosmic feedback on grand scales. As jets inflate lobes, they displace and heat surrounding gas, preventing it from cooling and collapsing into stars. In galaxy clusters, this process helps solve the long-standing cooling flow problem, where hot gas should cool rapidly and form stars at rates far higher than observed. Instead, repeated outbursts from central radio galaxies inject energy into the intracluster medium, maintaining it in a hot, diffuse state. Cavities carved by radio lobes are visible in X-ray images as dark bubbles, silent testimonies to past episodes of AGN activity. The lifetimes of radio galaxies are finite. Jets do not run continuously. They turn on and off as accretion conditions change. When a jet shuts down, the radio lobes begin to fade as their relativistic particles lose energy. Over time, the galaxy may enter a quiescent phase, leaving behind ghostly relics detectable only at low radio frequencies. In some cases, jets can restart along a new axis, creating double-double radio galaxies that preserve a record of multiple active epochs. These layered structures allow astronomers to reconstruct the duty cycles of AGN and the episodic nature of black hole feeding. When viewed within the broader AGN family, radio galaxies occupy a specific orientation niche. In unification models, an FR radio galaxy observed edge-on may appear as a quasar if viewed down the jet axis, its core emission boosted, and its broadline region exposed. An FRI radio galaxy, viewed along its jet, may appear as a BL-lac object, characterized by rapid variability and weak emission lines. Thus, radio galaxies are not isolated species, but part of a larger continuum, their appearance shifting with perspective. Together, active galactic nuclei and radio galaxies illustrate the extraordinary reach of black hole physics. A supermassive black hole, smaller than the solar system, can govern processes on scales of galaxies and beyond. Through radiation, winds, and jets, it can regulate star formation, sculpt the intergalactic medium, and imprint its presence across millions of light years. AGN are the engines. Radio galaxies are among their most dramatic exhaust plumes, visible markers of energy flow on cosmic scales. In these systems, gravity, electromagnetism, and plasma physics converge. Matter falling inward powers energy streaming outward. The smallest and largest scales of the universe become linked, bound together by the physics of accretion and feedback. Active galactic nuclei remind us that galaxies are not closed islands of stars, but dynamic systems whose centers can awaken and, for a time, dominate the cosmic landscape with jets of light and force that reshape the universe around them. Giant radio galaxy lobes are the farthest-reaching expressions of black hole power ever observed, colossal reservoirs of energy inflated by relativistic jets that have escaped the confines of their host galaxies and spilled into intergalactic space. While the active nucleus and its jets occupy relatively compact regions, the lobes they create can extend for millions of light years, dwarfing the galaxy that launched them. These lobes are not merely passive clouds of debris, they are long-lived structures filled with magnetized plasma and relativistic particles, glowing faintly in radio wavelengths as they slowly dissipate the energy injected by the central engine over tens to hundreds of millions of years. A giant radio lobe forms when a powerful jet maintains its integrity over vast distances, transporting energy efficiently from the vicinity of a supermassive black hole to the outskirts of the cosmic web. As the jet plows through the surrounding medium, it drives shocks ahead of it and inflates a cocoon of hot plasma around its path. At its termination point, often marked by a bright hotspot, the jet's momentum is finally dissipated, and its energy spreads sideways, filling an expanding lobe. Over time, these lobes grow, buoyantly rising through the intergalactic medium, and sometimes detaching from the jet entirely as relics of past activity. The scale of giant radio lobes makes them sensitive probes of their environment. Their shapes, asymmetries, and spectral properties reflect the density, pressure, and magnetic fields of the medium they expand into. In dense cluster environments, lobes may be confined, distorted, or deflected by the surrounding intracluster gas. In lower density regions, along cosmic filaments or voids, they can expand more freely, achieving truly enormous sizes. Some of the largest known radio galaxies span more than 5 million light-years from end to end, making them among the largest single objects in the observable universe. Despite their faintness, radio lobes carry a tremendous amount of energy. The total energy stored in a giant lobe can rival or exceed the binding energy of the host galaxy's interstellar medium. This energy is deposited not in a sudden explosion, but over prolonged periods, gently heating and stirring the surrounding gas. In clusters, this heating can prevent hot gas from cooling and collapsing into stars, providing a long-term regulatory mechanism that complements more localized AGN feedback. On intergalactic scales, lobes may seed magnetic fields and relativistic particles into regions far from any galaxy, contributing to the magnetization of the cosmic web. Giant radio lobes also preserve the memory of black hole activity long after the central engine has quieted. Even when the jets shut down, the lobes can persist as radio ghosts, slowly fading as their particles lose energy through synchrotron radiation and inverse Compton, scattering with the cosmic microwave background. At low radio frequencies, these relics can still be detected, revealing past episodes of activity that would otherwise be invisible. In some cases, new jets ignite along a different axis, while old lobes remain, creating layered or misaligned structures that record changes in black hole spin or accretion geometry over cosmic time. If giant radio lobes represent black hole energy released outward into the vastness of intergalactic space, then ultra-luminous infrared galaxies, or ULRGs, represent energy buried inward, smothered in dust and gas as galaxies collide and ignite intense internal activity. A ULRG is defined by its extraordinary infrared luminosity, exceeding 1 trillion times that of the Sun, most of it emitted not as visible starlight, but as infrared radiation from dust heated by prodigious star formation, and, often, an active nucleus. These galaxies are among the most luminous objects in the local universe, yet many are nearly invisible in optical light, their true power concealed behind thick veils of dust. ULIRGs are almost invariably associated with major mergers between gas-rich galaxies. As two spirals collide, tidal forces drive vast quantities of gas toward their centers, compressing it into dense regions where star formation proceeds at astonishing rates. Hundreds or even thousands of solar masses of stars can form each year in compact nuclear regions only a few hundred parsecs across. The intense ultraviolet radiation from these newborn stars is absorbed by surrounding dust, which heats up and re-radiates the energy in the infrared. The result is a galaxy that glows brilliantly at long wavelengths, even as its optical appearance may be chaotic, distorted, or obscured. Embedded within many ULRGs is a growing supermassive black hole, fed by the same gas inflows that power the starburst. In some systems, the AGN contribution dominates the luminosity. In others, star formation is the primary source. Often, both coexist, tangled together behind dust, so thick that disentangling their relative roles requires observations across the electromagnetic spectrum. X-rays, infrared spectroscopy, and radiodiagnostics all contribute pieces to the puzzle, revealing buried nuclei, outflows, and extreme physical conditions deep within the merging cores. The environments inside ULIRGs are among the most extreme known in galaxies. Gas densities are enormous, turbulence is intense, and pressures far exceed those in normal star-forming regions. Under these conditions, star formation may proceed differently, with a top-heavy initial mass function favoring the formation of massive stars. Supernova rates soar, injecting energy into the surrounding medium and driving powerful winds. These winds can blow out along the galaxy's minor axis, carrying dust, gas, and metals into the halo and beyond. In some ULRGs, molecular outflows have been observed with enough mass and velocity to significantly deplete the central gas reservoir, signaling that the starburst and AGN are actively dismantling the conditions that created them. ULRGs are often interpreted as transitional objects in galaxy evolution. In the merger-driven scenario, two gas-rich spirals collide, ignite a ULRG phase marked by intense star formation and obscured AGN activity, and eventually exhaust or expel their gas. As dust clears and star formation subsides, the remnant may emerge as a quasar or a massive elliptical galaxy, its stars now old and its central black hole fully grown. In this view, ULIRGs represent a brief but crucial phase in the transformation of disk galaxies into spheroidal systems, a phase when much of the stellar mass and black hole mass is assembled rapidly. Although ULRGs are rare in the nearby universe, they were far more common at earlier cosmic epochs. At redshifts of 1 to 3, when galaxy interactions were more frequent and gas fractions higher, infrared luminous systems dominated the cosmic star formation rate. Many of the massive galaxies seen today likely passed through ULIRG-like phases in their youth. Studying local ULIRGs, therefore, provides a window into the processes that shaped galaxies during the peak era of cosmic star formation, allowing detailed investigation of conditions that are otherwise accessible only in distant, faint systems. The contrast between giant radio galaxy lobes and ULIRGs highlights two extremes of energy flow in galaxy evolution. In one, energy escapes efficiently, channeled outward along jets that inflate structures on intergalactic scales. In the other, energy is trapped, absorbed by dust, and re-emitted locally, reshaping the galaxy from within. One sculpts the environment far beyond the host. The other transforms the host itself. Yet both arise from the same fundamental engine, gravity driving matter inward toward a supermassive black hole or into dense star-forming regions, releasing energy that must go somewhere. Together, these phenomena reveal the dual nature of galactic power. A galaxy can shout into the cosmos through colossal radio lobes, marking its presence across millions of light years. Or it can burn fiercely in obscured silence, its brilliance hidden in infrared wavelengths as it forges stars and black holes behind walls of dust. In both cases, the energy released reshapes matter on scales far larger than the processes that generated it, demonstrating that galaxies are not passive collections of stars, but dynamic systems whose influence can extend deep into the fabric of the universe.